feel like you're leaning.
That's all right. I have one also. We'll both read. Go ahead. You start us.
Newton's third law? What do you want me to read from?
Page 138, number 2.
Oh, okay.
We're just going over example
Net
problems.
external force on a golf cart is 390 N North.
Which stands for? What's forces? Newtons. Very good. Continue.
If the car has a total mass of 270 kilograms, what are the magnitude and direction of its acceleration?
So the mass is 270 kilograms, and the overall force acting on this object is north, and it's 390 newtons. Oops. Let's just say, we'll call it F for now, because it's not F1 or F2. And the overall force is 390 newtons. Now, the problem says find the magnitude and direction of the resulting acceleration. It's a pretty simple problem because there's one calculation. But the idea of the magnitude and acceleration, or direction, let's discuss. The magnitude means what again? What does the magnitude of the acceleration mean?
Absolute value.
Yeah, the actual value, the absolute value of the acceleration. And then the direction means north, south, east, or west. So if the overall force acting on this golf cart is north, which way is the acceleration going to be? North. If I push to the right and the object moves, where is it going to move? It's going to move to the right. Okay, an object at rest, when forced to the right, moves to the right. So acceleration and force are in the same direction. This is back to our idea of a vector. Okay, so the idea here, we have a force acting north with 390 newtons, a mass of 270 kilograms. Let's go ahead and use Newton's laws. Okay, which of Newton's laws can we use here? And how can it help us determine the actual acceleration of the body? Nina. Good. What are we going to solve for?
A.
So A is simply F over M. Okay, which is what your book defines, I think, acceleration as in the beginning there. Let's see if it says it. Oh, they don't even go into that. Okay. So acceleration, again, defined as the ratio between the force of an object, or force on the object, and the mass of the object. So if we simply divide our two numbers here, we'll get a quotient. Okay, we should get around 1.4. I think it's 1.4 repeating is the number for this one. Our force is 390, our mass is 270. It turns out to be around 1.4 meters per second squared. Now, this is really just the magnitude. What do I have to tack on to the end to give direction? It's not negative, it's north. Okay? It's not negative, guys. Again, negative means an object is either moving down or you would say south. But this is an object with an overall force acting upward, okay, or acting north. In this problem, I drew north is up. Okay, acting north. So this is the magnitude here, but if we wanted to write out the entire thing, we should really put a north symbol down. I'm not used to this stylus, sorry. Okay? So acting to the north, because again, the force is applied north. If the force were applied west, we'd say west, etc., etc. The important part right now is understanding the idea that quickly you can be given an overall force on an object and its mass and determine the acceleration. In the lab, what did you see with this? What did you notice? What was your correlation that you picked up on in the lab? When you looked at, like, there was the dog, the book, the refrigerator, the crate. What was the general consensus that you came to as like a summary as to what you did with the pushing and stuff? What happened there? Give me an idea. Give me something. It doesn't have to be exactly right. Julian.
The object with less mass would be further.
Yeah. Or faster and easier, right, in general. So more mass means it's tougher to push. The same thing we're saying here again. Okay, again, the acceleration here is a function of the mass and the force on the object. And the force on the object. What did you notice in the second part of the lab when friction existed? Sometimes you would push and what would happen? Yeah, it didn't move at all. Who could explain that? What's going on there exactly? Give me some, Tori.
Like, I don't know, like, the technical thing of this, like, the ground and, like, air resistance and stuff is stopping it. And it takes longer to, like, gain, like, you have to gain more momentum to get it going.
Yeah, so it takes a lot of force to get it past that static friction, which we'll talk about in the next section with friction, and then it takes more to get it going and keep it going because of friction, okay? Because of friction. Let's see if there's another one I want to look at.
When is that lab due? It's not due tomorrow.
That lab, what we're going to do is tomorrow we're going to spend about 10 minutes discussing it. So if you didn't finish it tonight, or if you didn't finish it, you should really work on it tonight. Okay, we'll spend about 10 minutes discussing it tomorrow, and then either I'll collect it or I'll take a quick look and check to make sure everybody did it. Haven't decided yet. But you should assume it's due tomorrow for you guys, just to have it, for the most part, done. There isn't much more. It was 3 pages, right? Yeah, and most of you finished the first 2 already. So work on getting those conclusion questions done at the end. Okay, and we'll discuss it tomorrow in class. And then either I'll give you a future date, I'll collect it, or I'll just check to see that you did it. I really want to focus on the next lab, which is a little more important than that one, which is still in chapter 4. Let's take a look at number 4 now on page 138. Number 4. What I would like you to do is, as I read it, to draw a diagram. Okay, draw a diagram from what I'm telling you, and I'll try and read slowly. This is page 138, number 4. A 2-kilogram object starts from rest at the top of an inclined plane. A 2-kilogram object starts at rest at the top of an inclined plane. When I see you just staring into space right now, you're not following directions. Again, you should be drawing what I'm actually saying and writing down information. So a 2-kilogram object starts from rest at the top of an inclined plane. An inclined plane is a ramp, in case you're wondering, because we haven't used that terminology yet. Okay, so I'll draw that part so we all know at least what that looks like. Okay, there's the ramp. So it starts at rest at the top. It says that the ramp is 85 centimeters long. 85 centimeters long. And that the object slides to the bottom in a half a second. So the ramp is 85 centimeters long, and the object slides down in a half a second. We're not given any information about the angle, okay? So we're not going to be breaking into components. The question becomes, what is the net external force that acts on the object? What is the net external force that acts on the object? So who could give me a suggestion as to what I can start with my diagram? What can I do to start? And this is not drawn to scale, obviously. Let me just draw a right angle so we can see that there. Okay. What could I do to start this one? Who's got a point of suggestion that we could start at?
Gravity.
Okay, what about gravity? Okay, gravity definitely pulls it down the ramp. Good, that's true. Okay, what else? Friction exists, okay. So for this object already, we're going to have, and this is tough because it's an inclined plane, so friction is going to act like this, right? It's going to act up the plane if we would draw the free body diagram for this one. And we'll talk more about the free body diagram for this tomorrow because there's more to it than just this. And gravity acts down. Good. And I think that's it, right? There's nothing else acting on this. It doesn't say there's a propulsion force or anything else at all. So that's it for the free body diagram. There's not much more you can draw. Okay? Nothing about it in the problem, no. Nothing about it.
What do we want to solve for x?
What do we want to solve for x?
Oh, never mind, no. Never mind, it's given.
X is given, yeah. What's the length of the ramp, people? Not 85. So what is it?
8.5.
What?
What is 85 centimeters?
Oh, 800.
Per second? Because it's only way half a second.
0.85 meters.
Alright, there it is. That's the first one I heard right. 0.85. You said 0.085, Tristan, and you said 8.5 back there. Okay, but you both said different things. So the length of the ramp is 0.85 meters. Remember, centi is 2 decimal spots. So 85 centimeters becomes 0.85 meters. Those are conversions. Now, you're also told that the time it takes to slide down the ramp is a half a second. Come on.
Is that supposed to be 2?
Yeah, I'm having trouble. It's a different stylus. I'm just getting used to it. Sorry. Okay, that's the time it takes to go down the ramp. What else is known?
Oh, the mass is 2.
Yeah, good. 2 kilograms. Mass is 2 kg. I know something else. Tori.
The initial velocity is 0.
Yeah, that's the key here. VI is 0. That helps a lot. How do we know it's 0? Starts at rest. Now, this is where it's getting tricky. In section 4.4, when we do some of these problems, we're going to talk about breaking it into components because of the angle it's going at, and this is theta. But this problem is not asking about any of that. We're just told it slides a certain distance along a ramp. So we could technically call 0.85 our x in this problem, our displacement. Okay? Even though in class, I know we've been saying x is along the x-axis, y is along the y-axis, and we will go into that detail in 4.4. But for this problem, we're not given anything about theta. So we don't know anything about the angular components. We have to think about this as an overall system. So we could simply say that x in this problem is 0.85 meters. Now, I want to figure out what the net force is acting on this object. If you want to find net force, what do you need using Newton's laws to find net force? What do you need? You need acceleration. So does somebody have a suggestion as to how I can find the acceleration in this problem? How can I find the acceleration in this problem?
Is it not negative 8.1? Something else?
It's not negative 9.81. Remember, an object freely falling is, but when you go down a slide at the playground, don't you go slower than gravity?
Okay.
So it's going to be something less than 9.81 for sure. It will most definitely be less than 9.81.
I will find the right equation.
How would I find the acceleration?
The kinetic equation.
Yeah, kinematic equations. Which one though? They all have acceleration in them, but two of them have something in them that we don't have.
The one with t squared.
No.
Why is that one with t squared? Why would you use that?
Because they're not final velocity.
Good. The other two equations involve final velocity. We have VF equals VI plus AT. We don't know VF, so we can't do that. We have VF squared equals VI squared plus 2AX. We can't use that formula. So the kinematic equation that we're going to use is indeed x equals VIT plus 1/2 AT squared. Now remember that this is the general displacement, not the displacement in the x direction or the y direction. Okay, this is just displacement in general. What do we know? What can we drop off right away?
VI.
Yeah, because VI is 0. So put an x through that, get rid of it. If I wanted to solve generically for A, what would that become? How do I get rid of 1/2?
2x over t squared.
Okay, multiply by 2 to start. Good, to get rid of the 1/2. Then get rid of the t squared by dividing. Okay, there's acceleration. So acceleration is 2x over t squared. Yes?
Hey, you can get rid of the square.
Can you get rid of the squared? No, I wouldn't get rid of the squared because you're not solving for t.
Oh.
When you're solving for time, you would take the square root to get rid of it. When you're not solving for time, you have the time. Okay? So let's plug into this now.
Because T is 1 now, so wouldn't it just...
T is not 1. T is a half.
No, but didn't you multiply by 2, so no.
I didn't. I multiplied the x by 2. That's all right.
The half value.
It's okay. So, yeah, it's 2 times 0.85 over the quantity 0.5 squared. What do you get? What do you get?
1.7 over...
Yeah, 1.7 over 0.25. What does that come out to be? Come on, folks. The slower we go through this, the slower time we have to review for stuff. 6.8. Thank you, Gio.
I got the same thing.
You cleared it in. Now, what do you notice? The acceleration is bigger or less than 9.81? It's less than 9.81. Why is that again? Why is that? It's not a free fall. It's moving down A. And a ramp slows you down. If you go down a slide at the playground, instead of jumping off the top of the jungle gym, don't you go much slower down that slide? That's the idea, is to slow you down. That's the reason you go down slides, to slow you down. A ramp is there for that reason as well. When you're coming off of a moving truck, you don't want to just drop objects to the ground, right? They'll break, big boxes of things. So you go down a ramp and you slow down the motion. It's also to help you because it's less energy, obviously. It's a simple machine, a ramp. But the idea here is that we can tell that the acceleration's got to be less than 9.81. 9.81 is the greatest acceleration we can feel on Earth in a free fall situation. Obviously, if you have a jetpack on, you're aiming to the Earth to go faster. Okay? So that's the acceleration in this problem. Now, if I want to know what the overall force acting on the object is, what do I have to do?
Multiply the mass times the acceleration.
Very good, Aaron. So again, use F equals ma. So we use the 2 times that. So just double it, really. Okay, so double it because the mass happened to be 2 in this problem. And we'll multiply that by the acceleration. What would my units be for force? Yeah, newtons. And I can tell because it's, again, kilogram meter per second squared. That's the units of a newton. So what do we got? 13.6? All right, 13.6 newtons is our final answer. This kind of a problem is not easy because you have to incorporate your kinematic equations with your force equations. So you have to determine the acceleration first, and only then can you go on to figure out what the actual force is on the object. Again, in section 4.4, when we talk about things on inclined planes, we're going to be breaking into components with angles like theta, but this was just like a little preview in this chapter or this section, okay, as to see inclined planes.
You don't have to shoot it to just the grams or kilograms.
No, so let's talk about that real quick. The standard unit, you should probably write this down if we haven't talked about it already, which I guess we haven't if you're asking the question. The standard unit for mass is kilogram. It's not gram. Every other unit has no prefix, but the standard accepted international unit for mass is indeed kilogram. Okay? It is kilogram. So that's the only one that you're not going to change the prefix on, kilogram. Yeah, it has to do with the fact that, well, first of all, the measurements and where they come from. And a kilogram, if you look on Newsfeed, you'll see I put a link onto that as to how a kilogram is really defined and how its definition is changing. Say again? So a kilogram, again, you're not going to change the units there. You're not going to change the units to grams.
Would you ever give us it in grams out of 10 kilograms?
Sure. So imagine you had like 500 grams. That would be a half a kilogram because 1,000 grams makes up a kilogram. Okay? So you could have to convert from grams to kilograms, but you're never going to have to get out of kilograms. Okay? Let's take a look at number.
But the only confusing thing is, like, you take the kilograms, the mass, and then you use, what was the distance again? Meters.
Meters per second squared?
Yeah, you don't use like centimeters.
No. And that's what I was saying before. It's a little bit misleading. Yeah. Page 140, number 3. Luke, nice and loud for us. Nice and loud.
Identify the action-reaction pairs in the following situation.
Give us part A first. This is part
The
A.
person takes a step.
All right. So I take a step, literally. I'm taking a step. What is the action-reaction pair that's existing here? Remember Newton's third law for this to help you. Take a step. What's physically going on?
The contact with the floor and your applied force
R.
and gravity and
You're giving me everything, but give me specifically what's causing me to step forward. Gravity is definitely helping, but my applied force pushes,
that way.
and what pushes me forward?
Your legs.
Not my legs. This is tough, right, to think about. I apply a force backwards.
You're pressing against the floor in that direction, which pulls you in this direction.
Yeah, so what's pushing you back?
Friction.
From the...
From the floor.
Yeah, okay. So again, I push to the left, believe it or not, when I walk. Well, in your direction, let's say, I'll walk left for this sake, okay? So I push to the right, and the floor pushes me to the left. That's how I move this way. Think about it. The only way you can move is by causing some sort of unbalanced force. The floor is what balances that out, okay? If I have acceleration, then it's different. Then I'm going to start changing my velocity, and I have an overall force. But again, the action-reaction pair is you pushing the floor pushing back. Next.
snowball hits someone in the back and the neck.
In the neck?
Sorry.
In the back or the neck, either one. So somewhere in the back of the body, a snowball hits somebody. Now, let's look at two scenarios. Scenario A, the person is standing still, it hits them in the back and they don't move. Okay, the snowball hits them in the back and it just explodes on their back and they stand there like, really? That didn't hurt. Scenario B, you throw a really, a heavier snowball, hits the person in the back, Luke throws it this time, hits the person in the back and it knocks them forward. Okay? Two scenarios. Scenario 1 first. Scenario 1 first.
So if I hit you with a snowball.
The force in which you throw the snowball is less than the total mass of that person's body.
Okay, you're using terms that are not able to be interchangeable. Give me the action-reaction pair, though.
The force of the snowball.
Is action good? What's the reaction?
Reaction is how the, what do you mean, like, hit the person, if he moves or not.
No, we're looking at the action-reaction pair of forces, not the overall result. What are the forces that are acting on the scenario?
The back.
The person's back, pushing back. So like, for example, a snowball hits you in the back, and if you just stand there, it means that your back pushed with the same force back against the snowball, which caused it to either fall to the ground or explode. But if a snowball hits you in the back and it knocks you to the ground, did you have enough force to push back with? No, you didn't. So now you're falling forward. Now you're falling forward, so maybe your force stops you. So that would be your reaction actually to stop you. Okay, so it's not necessarily on the exact time of collision that you're going to see that reaction there. So a snowball hits you, and the force of the snowball is more than you could withstand, you would fall down. It would knock you over, and either the ground would stop you or your feet hitting the ground like this would stop you. Okay? That's the idea here. Again, I'm not asking you to give me the whole scenario. Like Julie before described gravity and everything, and gravity is incorporated friction, but the answer before is just you push the floor pushes back. Snowball hits you, you hit back. Let's take a look at C. Julie, you want to read C for us, please? Or C?
Julie.
Julian.
A baseball player catches the ball.
Alright, so the simplest example is a catcher in baseball. Think about it. When a catcher crouches, he or she puts his glove or her glove in front of him or her, right? That's what happens there. And then the ball or the softball comes in, it hits the glove. Why doesn't the glove just smack the person in the face? Yeah, their hand is exerting what? Force, backward. That's all it is, or forward, whatever you want to call it. But the baseball hits the glove with a certain amount of mass and acceleration, and then if you can respond with that same force, it's what able to stabilize the ball. If every time the ball hit the glove, the catcher of the glove went flying, would baseball exist? It wouldn't even make sense, right? You'd be sitting there all day. So again, the idea is that you need to provide equal and opposite force to slow down that baseball in a certain time period. Now, clearly the glove might move a little bit, right? So you have some sort of give, and that's normal. But the idea is that you provide equal and opposite force. Let's look at the last one I think is the most interesting one to look at. A gust of wind strikes a window. So imagine here's a window right here, and I turn on a fan. Clearly, fan pushes air, right? So there must be force involved. How does that work? A gust of air hits the window. What's going on, James?
But this is kind of weird though, because wouldn't that be like thousands of tiny impacts?
So tell me more about that. That's exactly what I was getting at, James. Talk about that. What do you mean thousands of impacts?
Well, I mean, each air molecule is a separate impact on the whatever window.
So we would say that this is not just a force, but a force that is what over an area? What's the word we're looking for? The force is being what over this area? It's what?
Distributed.
Yeah, distributed. It's a distributed force. Okay, and we're going to talk about this. And in engineering, you have point forces, which are like concentrated forces, and distributed forces. They're called load forces. So a building or a bridge is definitely a distributed area, or distributed forces. Because each car that's on the bridge is like an air molecule hitting that window. Every car pushing down on the bridge is like a little force of its own. So you can look at the overall distribution of forces on the bridge. It's the same thing as air. If air hits the window, it's not hitting the window here. It's not hitting it here. It's not hitting it here. It's hitting it everywhere. And that's really what the definition of pressure is. And we'll talk more about pressure when we get to fluids and mechanics.
Is that why a needle would be able to get like into your skin and stab you? But if you had like a bed of needles, you would be able to just lay on
That's
them.
exactly right,
It's
Julian.
distributed over an area.
And that's to do with the pressure, yep. The higher the pressure, Okay, over a smaller area in order to like poke through in that sense.
Do I have a free?
So tomorrow, guys, again, please tonight take a look and finish up your last things for your lab. You can already do 4-1, 4-2, and 4-3 of problem set for the next week. You should get started on that because 4-4 is very tough. Get started on 4-1, 2, and 3 for your problem set for the next 3 days.
I didn't take it. I know.
4-3 and 4-4 is very difficult.